Okay, can you hear me? Everything is okay?
Yeah, I can hear you.
I think it works very well.
Okay.
Yeah, perfect.
Okay, so welcome everyone to this Mersorcium seminar. And yeah, I think we will just start directly to Javier presentation, and I will let you presenting yourself and telling us all you know about isotopic tracer.
Okay, today I'm gonna talk about isotopic tracers as a powerful tool for the determination of microbial mercury species transformations. And first, we will introduce the topic, what is an isotopic tracer, the concept of isotope dilution analysis, after the main uses, how they can be used for determining natural, inorganic, and methyl mercury by GC-ICP-MS, gas chromatography, coupled to inductive coupled plasma mass spectrometer. And also we'll see how we can use them to study the mercury compounds reactivity and the main problems associated with mercury incubation experiments. After, in this second part, we will see the experimental approach that I used during my PhD for pure phytoplankton cell cultures. And we'll talk about two main methodologies that I developed during my PhD, the quadruple isotope spiking, the key points to consider, and the newly formed volatile mercury compounds, another methodology to quantify the volatile mercury compounds. And finally, we will see the potential application. Okay. Before starting, today I'm gonna talk about mercury compounds: inorganic mercury, methyl mercury, gaseous mercury, and dimethyl mercury. In my case, for me, mercury species is the complexation of inorganic mercury and methyl mercury with the dissolved organic matter, chloride, and so on. So today, I will talk only about mercury compounds. So first of all, I'm going to introduce myself. In 2017, I finished my bachelor degree in chemistry at the University of Oviedo. There, I also did my master degree in analytical chemistry. And to sum up, my master thesis was about the determination of melatonin and its oxide metabolites by bidimensional liquid chromatography coupled to electrospray ionization tandem mass spectrometry. On October 2018, I started my PhD at the University of Pau under the supervision of David Mogo and Zoe Pedrero. During my PhD, I had two main goals. The first was the improvement of the analytical methodologies for the mercury compounds transformation through the use of isotopic tracers. And the second, the investigation of the major intercellular bioligands involved in mercury speciation in phytoplankton cell cultures. Today, we will talk about my first objective. Also, during my PhD, I could carry out my international mobility in the environmental biochemistry and ecotoxicology department under the supervision of Professor Vera Slavikova, where I could expand my knowledge about the microbiology of phytoplankton and ecotoxicology. Nowadays, I'm working as a ICP-MS application specialist in my hometown, in Gijón, in a company called Innovative Solutions in Chemistry. Okay, so now let's talk about science. First, we have to answer this question. What is an isotopic tracer? An isotopic tracer is an element which is enriched in one of its isotopes. It's important to point out that the chemical behavior of the different isotopes is independent from its mass. For example, you can see here the isotopic distribution of mercury isotopes, the natural one. And as you can see here, we have the inorganic mercury 199, who is enriched in that isotope, but also you can see that you have other contributions. The intentional alteration of the isotopic abundance of an element can be used for two purposes: as quantification tracers for the determination of natural mercury compounds by isotope dilution analysis, or they can be used as incubation tracers to investigate the mercury compound reactivity and fate. So first, we will explain the concept of isotope dilution analysis. The concept of isotope dilution analysis is based on the modification of the isotopic composition of an element by the addition of this element enriched in one of its isotopes. For example, here we want to determine how many black balls do we have. In this case, the black balls represent the natural inorganic mercury, and we add a known amount of blue balls, in this case, the enriched isotope inorganic mercury, and we wait for the isotopic equilibration. After this isotopic equilibration happens, we can take an aliquot, and knowing the proportion between blue balls and black balls, we can determine how many black balls, or in this case, inorganic mercury, we have. Now we are going to move to the dipole isotope spiking, where we have in our sample natural inorganic mercury and methyl mercury, and we want to quantify them by adding the inorganic mercury enriched in the 199 and the methyl mercury enriched in the 201. So the gas chromatography, it is used to separate both mercury species, and after we have elemental ionization source coupled to a mass spectrometer. In this case, it's normally the quadrupole that is used as a mass analyzer. What's the main problem with this sample preparation? Here in this sample preparation, we have a derivatization step that can degrade the mercury compounds. I'm hearing a sound, but it's okay. I'm gonna just keep talking. So during this derivatization step, you can have methylation or demethylation of both mercury compounds, but also some mercury losses due to incomplete recoveries. Because of that, we have the advantages of isotope dilution analysis. Once the isotopic equilibration is achieved, any loss of sample during the sample preparation will not affect the final results. But also, any variation in the sensitivity due to instrumental stabilities will have no influence on the final concentration. The other use of the isotopic tracers is to study the mercury compounds reactivity. Once we add the incubation tracers, we can have the methylation, demethylation. Inorganic mercury can be reduced into elemental mercury. Methyl mercury can be reduced also through a two-step process or one-step process, but also both original mercury compounds that we added can be or double methylated or methylated one time and forming dimethyl mercury. So based on that, we are going to see the main problems in mercury incubation experiments. The main problem is that the mercury compound transformation yields are not universal, and in most cases, they cannot be compared with other studies. Here we have the first step that we add the incubation tracers. After this process, we add the quantification tracers for mercury analysis, and in this step, is where you use the isotope dilution analysis, the analytical methodologies, to quantify the mercury compounds concentration, and then we can determine the mercury compounds transformations. But why? We have these problems? Why these transformation yields are not comparable? There is no agreement between laboratories. They use different analytical methodologies. Also, I haven't in the literature review that I carried out during my PhD, I didn't observe any analytical methodology assessment to show the for the mercury incubation experiment with 4 enriched mercury stable isotopes. And this is important because we have to better clarify the mathematical approaches and the analytical methodology used to determine these concentrations. And so far, no analytical methodology have ever distinguished the methylation and demethylation reaction between the incubation process and the sample preparation. Also, it's important to point out that for the determination of mercury compounds transformations, we need the concentration. So it's crucial to know how we quantify these mercury compounds. And after, we have a huge experimental variability, such as the spike addition, the incubation time, the pre-equilibration or non-equilibration of the mercury compounds before addition. And the final point is that we use in some cases, the same wording for the different mercury compounds transformations. For example, methyl mercury demethylation. In some cases, you can measure the methyl mercury demethylation as the decrease of methyl mercury concentration. This decrease in methyl mercury concentrations can be due to the precipitation, can be due to the formation of elemental mercury, the formation of inorganic mercury, or even the formation of dimethyl mercury. In some cases, they use methyl mercury demethylation referring to the formation of gaseous mercury or inorganic mercury, but in some cases, it exists a big misunderstanding when we refer to methyl mercury demethylation. So based on that, I'm gonna explain the experimental approach that I carry out in my during my PhD. Here we can see two phytoplankton strains. One of them is prokaryote, the Cyanobacterium synecocystis PCC6063, and the eukaryote diatom Cyclotella meningeriana. And we incubate them with inorganic mercury 199 and methyl mercury 201. As you can see here, the cells were exposed in exposure medium composed only for major cations, and we added 600 ppt and 60 ppt of inorganic mercury and methyl mercury respectively. We collect the samples at T5 minutes, 24 hours, and 72 and 96 hours of mercury exposure in the bulk but after we carry out a centrifugation to collect the cellular medium and the whole cells. And finally, we fractionate the cells in order to collect the cytosol and the membranes and cell debris. Why I have this red arrow? Because the mercury compounds transformations can be only determined in the bulk. Why? Because during the first centrifugation process, we have mercury losses. And when we break the cells, we also have some mercury losses. Because of that, it is mandatory if you have mercury losses during the centrifugation steps to only determine the mercury compounds transformation in the bulk. Based on this information, we are going to move to the third part, that is the quadruple isotopic spiking. As you can see here in this experiment, with the incubation tracers as the 202 inorganic mercury and 201 methyl mercury. And for the quantification tracers are the methyl mercury 199 and inorganic mercury 198. So first, we add our incubation tracers, and we have an incubation process that we will have a methylation or demethylation of our mercury compounds. And after, we have a second process for of the sample preparation where we add our quantification tracers, and we will have these interconversion reactions. As you can see here, all of the mercury compounds that we have here, the original and newly formed, it will happen the same, the methylation and demethylation process that occurs to the quantification tracers. And finally, we inject our organic solving in the GCI-CTMS in order to quantify the mercury compounds and determine the mercury transformations. As you can see here, this is the graph that you obtain, where in the y-axis we have the intensity, and in the x-axis we have the time that the chromatography separation for methyl mercury and for inorganic mercury. And with the ICP, we can measure all the isotopes. What is the objective now is to convolute the signal, know what is coming from which, in order, we want to separate its source. Thanks to the isotopic pattern deconvolution, we can do that. This value will be obtained by, for example, in this case, if we look at the inorganic mercury 198, we take this intensity and we divide it by the sum of all intensities. And the same with the 199, 201, and for methyl mercury is the same approach. Here, we only copy paste the isotopic abundance for the natural with the natural and or our 4 tracers. Once we get the molar fractions, we can apply in the concept that we saw in the introduction, the isotope dilution analysis, we can obtain the moles of each mercury compound. Here, it's important to point out that from this step, we can calculate the concentration, but they are not corrected. They are not corrected. First, we have to determine our methylation and demethylation yields during the sample preparation, and after we have to perform a mass balance to correct and recalculate the, the amount of moles that we have for each species. In the next slide, we are going to see what happens if we get the concentration directly from this process or taking into account these 2 steps. So we carry out a simulated incubation in the absence of the matrix. Here we have the ratio methyl mercury 201 and inorganic mercury 202, and we carry out 3 mixtures, 1,1, 3,1, and 10,1. And you can see here in this graph the methylation and demethylation yields during the sample preparation. If we move to the right part of the slide, we can see the concentration of newly formed inorganic mercury and methyl mercury. If we compare the corrected with the non-corrected, we can see an overestimation in the inorganic mercury 201, but also in the methyl mercury 202. But why these values are higher, or this overestimation is higher than for the inorganic mercury than for the methyl mercury? Because as you can see here, we have a higher demethylation during the sampling preparation. So these differences are higher. On the other hand, the methyl, we don't obtain significant methylation during the sample preparation, so these values are more similar. When we move to real samples, we have to be careful. We must perform a T0, where we acidify the sample first, and after we add the incubation tracers. This is important in order to check and eventually correct any unintentional methylation or demethylation reactions caused by the spike addition. When we applied this analytical methodology to our real samples, we can see here all the T0, and here we have 35 minutes of phytoplankton, T0. If we look at the T0, we can see the same pattern. We have an overestimation when we don't correct these interconversion reactions. In other words, we don't have a newly formed methyl mercury or inorganic mercury when we correct the analytical bias. And also you can see here that in biofilms and in sediments, we had methylation, but these values are similar. However, when we move to the inorganic mercury, as we saw in the last slide, these differences are higher. That means that during the sample preparation, we had like a high demethylation yield. So now there are other key points to consider. For example, the incubation times should be established depending on the ability of the method and instrument to detect newly formed mercury compounds. Also, you can pre-calibrate or non-pre-calibrate your mercury compounds, but that depends on the hypothesis tested. For example, if you want to apply, you want to investigate the potential transformation of bioavailable mercury compounds, you cannot or you should not pre-calibrate your mercury compounds, or even with a clean exposure medium. But also it's important to point out the endogenous background of natural mercury. For example, if we have a sample that contains like 2 ppb of inorganic mercury, you cannot add 1 ppt of your enriched spikes, because the goal is, well, first of all, it's important to put the isotopic enriched spikes at the same level of the endogenous background, but also you won't see any transformation because of these differences. Now, I wanted also to show you another methodology for the determination of newly formed volatile mercury compounds. Using the Purgreen system of on site of Dr. Bastien Doval, we could capture the gaseous mercury. This gaseous mercury has 2 isotopic signatures coming from the incubation of our original mercury compounds. So using the same approach as we use in the previous methodology, we can deconvolute the signal, knowing the molar fraction of the gaseous mercury coming from the 199 and the gaseous mercury coming for the methyl mercury 201. If we combine this deconvolution with an external calibration, we can achieve the simultaneous distinction of the inorganic mercury reduction and methyl mercury reductive demethylation pathways. And we successfully apply this methodology in surface lake waters and surface sea waters. So the conclusion, the 2 main conclusions of this part is that the quadruple isotopic spiking methodology developed has been successfully applied with concentrations ranging from ppq to ppb levels. But also the simultaneous distinction of inorganic mercury reduction and methyl mercury reductive demethylation provide a versatile approach to compare different compound-specific reduction pathways. So now let's talk about the potential applications. Here, these experiments, I did not carry out these experiments, but I think that it's worth it to watch it and after discuss it all together. For example, if we add or enriched inorganic mercury 199 to a cell culture, we can and we expose the incubation time is 24 hours. We obtained 100 ppts of methyl or newly formed methyl mercury 199. So we have a 50% of methylation. But what I was wondering is if we add 400 ppt, we will have 200. If we add 800, if we add 1,600 ppt, we will obtain the same values. Here we will obtain the double. So based on that, if I were to start my PhD again, I will try to, if I were working with a single organism, first of all, I will carry out this experiment. And this is what I expect to happen. Why? The methyl mercury formation depends on the bacterial metabolic activity and the inorganic mercury availability. So we are increasing the concentration of inorganic mercury, but at one point, it doesn't matter. It doesn't matter how much inorganic mercury you add. That you will have, or you would have, the same production of methyl mercury. Maybe in some cases you can have a suppression. But what is important? That maybe depending on the inorganic mercury concentration, maybe you can have two different methylation yields. Here we can see a line where the y-axis is the methyl mercury, the b would be the slope, and the x would be the inorganic mercury concentration. The A would be 0 in this case, because if we don't have inorganic mercury, we shouldn't have the methyl mercury formation. So in this case, the methylation this yield would be would have this form of this equation, and this could be the slope. And after, depending on the incubation time, you can even multiply this value by the time that you expose your mercury, your inorganic mercury. But what else? Also, it can be used to test a known hypothesis. The same, if we want to know if the methyl mercury formation is controlled by the abundance of the HGC AB transcript express, we can also carry out this type of experiments. The same approach can be applied to environmental samples. Another example would be to use different isotopes. We can add a certain amount of inorganic mercury 198. After, we can add a certain amount of inorganic mercury 199, and so on. In this case, we can obtain several methyl mercury formation rates, and we can even compare this step in function of the endogenous mercury background. Maybe these methyl mercury formation yields are similar, or it would be different. We don't know. Another example is if we want to, for example, know if your bacteria will reduce mercury, and you can create like a solution with your different isotopes compensated with several ligands like cysteine, glutathione, or disulfide marker. Once we add it, we can capture the gaseous mercury as we did during my PhD. You can deconvolute the isotopic signature, and you can obtain the simultaneous determination of inorganic mercury reduction in function of the mercury complex, just in one single experiment. You don't need to carry out different like cell cultures. So, as we saw in this presentation, we were only working with 5 isotopes, but it's important to point out that we have the 196 and the 204 that we can work. That means that the possibilities are even greater. So based on that, I would like to answer, my last slide would be is to answer these questions. Also, this question is why these methodologies and potential approaches are important for the mercury community. Basically, we should have an agreement between mercury laboratories in order to promote the best methodologies in the detection and identification of mercury compound transformations. That will allow us to rely on the results provided and compare and extrapolate between different laboratory studies. And also, I think I would like to remark that the combination of isotopic pattern deconvolution and isotopically enriched mercury isotope provide a versatile tool and new potential approaches to carry out new type of experiments in order to test a known hypothesis. Thank you. Finally, I would like to thank all of my collaborators from the University of Oviedo, University of Pau, and the University of Geneva. That thanks to them, I could carry out my PhD. So that's all.
Thank you very much. Very nice presentation. Thank you. So I think now we can move on the question. I think there is Clara that asked one. Carla, sorry. But please, like, if you have question, you can also just put your video on. We can be a bit more interactive if you want to. I don't want to force you, of course, but I think it can be nicer. Hello, Carla. So I think it was a bit dense. I don't know how you are familiar with the isotopic tracer that we can use. I have many questions, but I will probably start first with the question of Carla that asks, how do you know what you have mercury loss in the centrifugation step? Do you know what is the reason of these losses when you do the preparation of your...
You quantify your, for example, you compare the concentration that you obtain in the bulk, and after the concentration that you obtain in your extracellular medium and in your pellet. And if the sum of your extracellular medium on pellet, the concentration, or even you can do it in mass, it's equal to your bulk, that means that you don't have mercury losses. And why you can have, theoretically, when you do a centrifugation step, is like physical movement that can promote this evaporation of gaseous mercury. So maybe in some, I remember that Joao was testing that, and if you decrease the temperature of during the centrifugation step, maybe you can somehow avoid these losses. But this is quite tricky because mercury is really difficult to achieve that with mercury.
Okay. So anyone? I have some question. I will start and I will open it. So on the beginning of your, I have like one thing here. So I have a question from Cynthia, if I'm not wrong. It looks like you are working to quantify chemical isotope exchange in this experiment. Nice. Can you comment on how important that seems to be for methyl mercury isotopes? You have the question in the chat if you want to read it.
Yeah. When you talk about methyl mercury isotopes, you mean like the isotopic fractionation? It's just to know. Because so when you can.
Hey, no, I'm
I
thinking
need to. Okay.
Can you hear me?
Hi. Yes, I can hear you.
No, I'm thinking about whether there's chemical isotope exchange, perhaps between methyl 199 mercury and methyl 201 mercury, that has nothing to do with microbiology.
Isotopic exchange, if the methyl mercury 199 can become the methyl mercury 201, or the methyl mercury 201 can become the 199. No, I mean, I don't think so. And if it happens, it would be really insignificant, because we can see it with the recoveries when we quantify our mercury species. So normally we should not have this kind of behaviors.
I keep getting asked about that in our isotope work, and we don't see it either. But there are a number of people who think it might be important. So if you have a technique that clearly shows it's not happening, which I think you do, it's worth pointing that out when you go to write up the work, because there are several reviewers who may ask you about that.
Maybe they are mistaken with the isotopic fractionation. I don't know, because
I don't think so.
Kind
But
of, I don't know.
Yeah, it's worth thinking about. Yeah.
Yeah.
Thank you.
Thank you for your question. And now I have another question from Jan that says, if you spike different mercury, inorganic mercury, or develop mercury complexes with different enriched mercury isotopes, you need to consider isotope exchange rates. have you looked into this? I think that isotope exchange between methyl mercury and diphenol mercury is slow, but it can be fast between diphenol mercury and a mercury gaseous compound, elemental mercury.
Okay. Depending on, I think that it depends on your mercury complex, because let's imagine that we have a dissolved organic matter complexed with the 198 and I don't know, chloride of cysteine complexed with the 199. I think that you should be aware that you should not have excess of dissolved organic matter that the 199 can compensate. It's more about the no, that's not the word. Is that the speciation? I mean, when you prepare it, you have to be sure that all your mercury is complexed with dissolved organic matter, and all your cysteine is complexed with the inorganic mercury 199. Once you achieve that, you can have isotopic exchange, depending if the rates of the constants are similar, maybe, but if you have a dissolved organic matter complexity with the 199, after you have a chloride that is it's lower the affinity constant, I think that it's not that not happening. It's not happening. This is a hypothesis, but I think that it only happens when your constants of your complexes are similar. But if they are like you have different compensation or affinity constant, it should not happen. This is as a hypothesis.
Thank you. Maybe I can add a little bit to this, because I think that it is a relevant question, how fast different inorganic mercury complexes equilibrate isotopically. And I'm not so concerned about the methyl mercury, because I think this does not exchange very fast, or only very, very slow. But the inorganic species, I think they can equilibrate relatively fast. And then it depends maybe on the pool size, how much is the spiked pool versus the ambient pool that you look at. Mm-hmm. And I mean, your proposed experiments where you spike mercury cysteine with one isotope and glutathione and hydroxide species with different isotopes. If you do this and later want to investigate the reactivity of these different complexes based on the isotope that you spiked originally, then if you have isotope exchange during your incubation, then I think the data analysis will not work.
Will be wrong.
Yeah. So, and to my knowledge, there's very little work done on this. I mean, there's some experimental work from a group at Oak Ridge National Lab from Gu et al. And they have done some experiments, but unfortunately the analytical methods are not as good as yours. So I think someone with your expertise should do exchange experiments to really tell how fast different complexes are exchanging isotopically.
I see.
Well,
and if you know the chemical speciation.
Sure.
No, I was wondering if you know the chemical speciation of your system, and you know the percentage of your species that should be complexed with different types of ligands. I was wondering if you, I mean, in the end, it's all about equilibration. If you mimic a system, maybe you can, let's say, it's quite complex, yeah. But imagine that you have a specific spot in the aquatic system that you have, you know, the chemical speciation. You know all the ligands that are involved, and you can even replicate that in the lab and carry out this type of experiment, because in the end, it's all about equilibration. So it doesn't matter when what you add. If you leave it for a period of time, it will be more or less like you have in your system, right? In your natural system. The only point is that to replicate so to check all of this is quite complex.
Yes, thanks a lot. It was a very nice talk. I posted a link into the chat to a paper where this has been investigated in terms of isotopic exchange between different mercury 2 complexes.
Okay. Thank you. I have a question from that, because if I understood well, like really often you were saying that we should have like kind of an agreement between all the lab and like a methodology that we should use. And from now, like Jan mentioned the equilibration time, and you said like you mentioned the certain time for equilibration, like. What do you think? Like, how long could be like equilibration time when you do add like a tracer? Because I guess like after some time you can have just transformation happening. So I am myself sometimes just a bit lost with those kind of equilibration. Sometimes people will say 1 hour. Sometimes people will say overnight, and. So since you mentioned several times that we should have like a methodology that we should follow, what will be your best advice from the beginning until the analysis and until even like the deconvolution?
Yeah.
Like your recommendation, I would say.
Yeah. Depending is this pre-equilibration is highly depending on dependent on the matrix, because if you want to incubate in biofilms on sediments, or if you want lake waters, so it's kind of tricky. But in my case, the pre-equilibration, you can pre-equilibrate the time. No, it doesn't matter. The only point is that you have to collect one sample before the addition. Like that, you will know what you added. It can be pre-equilibrated or it cannot. You can take your mild solution, acidify, and well, normally you should not do that, but and add it. But you can prepare an intermediate solution. But the timing of pre-equilibration, or if you have more degradation during this time or less, it doesn't matter, because the important thing is that you know what you add. So if it's 1 hour or 2 hours, you take one adequate, and after I would add the isotopic tracers in order to know how much I'm adding.
And for example, what will you use as a, because I mean, you have like a certified tracers, like enriched mercury. So some people will use the certified numbers that we have from the supplier. Some people will just reanalyze the isotope in the lab before. Should we, in that case, analyze the relative abundance of your tracer from this after equilibration to make sure that you are avoiding to put any error in your deconvolution calculation?
For sure, you should characterize your spikes from the intermediate solution, because imagine that during your pre-equilibration you had your methyl mercury 201 was demethylated. This inorganic mercury, I mean, I'm gonna show you. I think that is gonna be, if I share this screen to answer this question. I think that with this table it's enough. Here. For example, imagine that your methyl mercury, I can add here a column, but well, imagine that your methyl mercury is enriched in 201, and after it's getting demethylated, and your methyl mercury is in the same solution that your inorganic mercury 199. This value, if it's demethylated, your inorganic mercury will be maybe 4, will be maybe 7, and well, this will change. It's because of that that this contribution during the equilibration can be corrected, because once you characterize your spike, even if it's it has been modified due to the demethylation of your methyl mercury, in this case 201, you will see it here. So you can obtain, you can take your intermediate solution and you can characterize your spikes, and you can even correct any demethylation that could occur during your precalibration time.
So you will recommend us to use a key, like the spike from like the intermediate solution that has equilibrated.
This is depending on the, I don't know which value I had, depending on the hypothesis tested, but normally, yes, I could imagine if I'm working with, in my case, so we were working with phytoplankton and we were using an exposure medium, a clean exposure medium, in order to avoid any change, and also the spike is acidified. If we add it, maybe we can stop the metabolic activity of the bacteria without knowing it. So yes, for sure, I think that the intermediate solution should be performed and recharacterized in order and check if you have any demethylation on your methylene or reduction of your normal organic mercury. You will know the concentration that you will add to your biological system.
So I have a question related to this. So do you think that this exchange of instant demethylation of the spike, you're talking about the demethylation happening in the incubation spike, but do you think it can happen as well as in the quantifying spike that you use in the lab when you use double spiking experiment?
So so you say that, imagine that you leave your mother solution like for 2 months, and your methyl mercury that you use for quantification is demethylated, right? And
yeah,
how you correct that? So okay, no, okay. So what you have to do is, what you should do is, here, when you characterize your spikes, you have to do it together, because if in this case, methyl mercury 199 was demethylated a little bit, it will be reflected in your inorganic mercury, but your inorganic mercury in the isotope 199, even if it's already enriched. But you can correct it if you characterize them together. It's what we were doing in Pau, that we were working with a methyl mercury was a little bit demethylated, and in order to correct that, we were characterizing the quantification tracers together.
But that's like this characterization should be done like very quickly after the preparation, because you said like, I mean, in 1 month, do you think that the relative abundance would change? I mean, it depends how you preserve your solutions and so on, right?
The
relative abundance, like,
but theoretically they are, they are separated. You say when you mix them, and it becomes that the methylation process, it changes the isotopic abundance, but if you can characterize them, even maybe you won't have the same, or you will have to check again the concentration of each isotope, or the possible demethylation of your quantification tracer. But you have to do it also depending on your intermediate solution concentration, or if it's in 1% of chloric acid. Normally with chloric acid, it's stable, but at ppm or ppb level, maybe ppt is quite. I don't think so. It's when you have.
I don't think so either. And also, I will continue. You mentioned the fact that we could estimate detection limit for the methylation and demethylation determination. I don't think I fully understood what you said with this ratio. After all, you said that we could do a correction, and I would like you to explain a bit more, if because I feel like it was not so clear.
So the detection.
Do you think there is like
you would like to know if you can determine the detection limit of a methylation or demethylation reaction? You cannot. You cannot. There is a paper who was talking about that. I think Hintelmann. I don't know if it was 1997 or 2003. I remember an equation, but I don't think so, because I've been talking with the people in Oviedo and I had the same question. And what they told me is that you cannot know the detection limit of a process of a transformation. What you can know is your methyl mercury or your inorganic mercury. And if they are above or below the detection limit, then you can apply the equation to determine. Because the detection limit in my case is you can only have it for a concentration, but not for a process. If your values that are below the detection limit, you should not apply these equations. Your equation won't be reliable. Is what I.
Yeah, I mean, this is, yeah, it makes sense. And also you mentioned like the application of those tracer that you can use. You spoke, because I mean, we are here speaking about microbes and how we can apply those tracers. And so I think the first example that you gave was about different concentration to test. And then you said that then you have like a threshold. We will not have like more reaction. But what if you have a too high concentration? You will probably reach a toxicity level that will even probably reverse all the functional. I don't know.
I
like,
totally agree. Yeah, sorry.
No, but I'm wondering then, like, what would be, so what you will suggest in that case, if you want to follow a microbial process, the methylation or demethylation of a solution of like a unique species or like a culture, I don't know. What level should we apply?
I mean, you first
of exposure.
Yeah, totally. If you want to, it's quite complex, because each microorganism has or its tolerance against inorganic mercury and methyl mercury. And for example, in this case, you want to see only the methylation. So in my case, I could do like PPT, PPB, and ppm level. And I could see if I have different methylation yields in function of the concentrations. And this is a test that it has never been, I think that it has never been done, because you don't know how the metabolic activity will be depending on the concentration. And after, if you want to, if your field is ecotoxicology, maybe you will have to increment the concentration. But if you want to see what is happening in the environment, maybe you have to decrease your concentration. But what is important is you have to be sure that the concentration that you are adding is what you are looking is what you have chosen. For example, many reviewers were maybe ask, why did you choose this concentration? So you can say, I did this study, and in this graph, I choose this concentration because it's at the level that I want to be. And with you working with the environmental sample, it's easy to answer like, yes, because we have the same level of endogenous mercury. But when you work with microorganisms and you didn't do any ecotoxicology test, I think that the experiment that I showed before, it's really important. I don't know the range of concentration, but you have to be sure that what you are looking at, and the only possibility is increasing the concentration and see if your methylation reaction is being modified by the amount of inorganic mercury available.
So by using different concentration for following those processes, do you think that so you said that it's possible that we can determine different potential of methylation and methylation? So
maybe I think it should be, yeah, it makes sense. Because
so if it's like it's a bit still, so do you have like some references, or like there is a paper
no, it's just
today for this
no, this experiment is just a hypothesis that I think that at what point the bacteria won't be able to produce more methyl mercury because of the toxicity induced by the mercury. But which is this point? Maybe you can carry out an experiment and you are adding a concentration that is above of that level and you don't know it, or it's below of that level. So I think that is an important test to do before doing kinetics or doing other things.
Okay, if it's still a
because
bit
you
like
are verifying. No, it's a hypothesis. It's a way to verify that you are giving the right values for that concentration, and you can prove that because maybe it will change with higher concentration or not.
But if it's like we are using tracers, and it can be like we can have different answers, and I mean those potential are used in modeling, in models and so on. So if it's like that, we might have like an order of magnitude of your potential, which is okay and it's good. But I was just wondering if we had like a good methodology that we can apply all together. And so that's what you suggested. We should have probably a methodological paper, or that's just probably review everything and suggest a method that we should follow, that we're sure that at least we compare something similar. Is it your point, or?
Yeah, when you work with, because we have biological samples and gravitas samples, but yes, it's my point, because with this methodology, first we know that we are quantifying, well, the inorganic mercury and methyl mercury, as we saw between the non-corrected and corrected mercury compost concentrations. And after, you have the mercury compost transformations, that they are highly dependent of the living organism. One is analytical and the other is biological. What's the point? Can you compare different methylation rate between organisms if you are exposing different concentrations to them? You cannot. Also, each microorganism will have a tolerance against inorganic mercury or methyl mercury or both. It's what I saw during my PhD is like there are a lot of unknown questions that should be verified to better explain what is happening inside the cell, or in terms of methylation and demethylation, and be able to extrapolate those data to the environment and so on.
Very good. Yes, well, it's 4 now. I mean, 4 in France, 3 in UTC. I have more questions. I think we can discuss of this isotopic tracer forever. I feel like sometimes it's just like, I don't know if it's really reliable tools. I mean, it's super good for internal standard and quantifying for sure, but for the processes, sometimes I'm always a bit skeptical. But yeah, I would like to thank you very much for your presentation, and I would like to thank you, all of you that were here. And like, I mean, if Cynthia put another comment, so with like a paper, so you can have a look about the mercury partitioning and concentration, that is very useful if you want to look and if people are interested. Thank you, Cynthia. But yeah, I mean, if anyone has more questions, I think you should send an email to Javier and ask more. It was super interesting. But yeah, I think I will just close this seminar.
Thank you so
and
much.
Again, thank you everyone. Thank you, Javier, for your really nice presentation. And I wish you all the best for this new position that you got. Congratulations. And yeah, hopefully I will see all of you again in a month. And I will wish you a very good day.
Ciao.
Hey.